In this lesson, we are going to learn about functions, relations, domain and range of linear absolute value, and piecewise-defined functions, union and intersection of sets, evaluating linear absolute value, piecewise-defined, and rational functions, graphing linear absolute value and piecewise-defined functions, and some real-life applications. Two things or objects can be related in many ways and can be expressed in different ways. For example, the name of students and their heights in inches can be expressed as a set of ordered pairs where Robert is 72 inches, Sarah is 61 inches, Matt is 70 inches, Robin is 61 inches, and another Sarah is 65 inches. The same set can be expressed in a table of values where one column represents the name of students and another column represents heights in inches. Another way to express this relationship is using mapping notation where names of students from the first set of values is mapped to heights from the second set of values. Note that the first set of values, the name of students, is the domain of this relationship, and the second set of values, the heights in inches, is the range of this relationship. We call this relationship a relation in mathematics. This relationship does not represent a function because there are two students with the same name Sarah and different heights of 61 and 65 inches. If we say, Sarah, what's your height? We get two different responses. However, if one of them is removed from the set, say Sarah with a height of 65 inches, then each name has a unique height paired with it, and this relation would also be a function. Note that 65 is removed from the range as no one is paired to a height of 65 inches anymore. Here's a function that maps x values to f of x and has a function notation f of x equals x squared. In this example, the name of the function is f of x, where it takes x and squares it. Looking at the graph of the function, we can see that f of x is a function because every x value is paired with only one unique y value. We can check to see if a graph represents a function by drawing vertical lines. If every vertical line drawn intersects the graph at most once, then the graph passes the vertical line test and represents a function. A graph of a function represents a one-to-one function if every horizontal line drawn intersects the graph at most once. We can see that the domain of the function uses all x values. Therefore, it is the set of all real numbers. We often use interval or set notation. The range of the function is from -1 to infinity, including -1, using a bracket. Since infinity and negative infinity are concepts, we never include them in an interval notation and use parentheses. We can use set notation to express the range as well. We read it as the set of all real numbers y such that y is greater than or equal to -1. In this example, f of x equals x squared is a function, but not a one-to-one function. Let's see if y is a function of x in this equation, and if it is a function, is it a one-to-one function? This equation represents a circle with a radius of 1. We can see that there is at least one vertical line that intersects the graph more than once. So the vertical line test fails, therefore y is not a function of x. If an equation is not a function, it cannot be a one-to-one function. We can also check for this algebraically. So first we subtract x squared from both sides. Then we take the square root of both sides. Note that we give one side plus or minus every time we take even root of both sides. Because of the plus or minus, there exists a value of x that is paired to more than one y. Say if x equals 0, then y is plus or minus square root of 1, so y is not a function of x. Though y is not a function of x, there is still a relation between x and y, and the domain and range of this relation is -1 to 1 inclusive. A relation is the way two things are connected or related to each other. A function is a relation where every individual input has a unique output. The collection of all inputs, or x values, that are defined by the function is called the domain of the function, and the collection of all outputs or y values defined by the function is called the range of the function. Vertical line test passes if every vertical line drawn intersects the graph at most once. And if the vertical line test passes, the graph represents a function. A function is one-to-one if each output comes from only one unique input. And horizontal line test passes if every horizontal line drawn intersects the graph at most once. And if the graph of a function passes the horizontal line test, then the graph represents a one-to-one function. Let's look at some sets and their union and intersection. Here, A is the set of all real numbers x that are less than or equal to 2, and B is the set of all real numbers x that are greater than -2. The union of A and B is denoted by a capital U between A and B. The union of A and B means the set of all real numbers that are either in A or in B or in both. The graphical representation of this union is the highlighted part in purple. The algebraic representation of this union is either x is less than or equal to 2 or x is greater than -2 or both, which yields the set of all real numbers. In interval notation, we get the interval from -infinity to infinity, and in set notation, we use the symbol for all real numbers. Now, the intersection of the same two sets, A and B, means the set of all real numbers that are in both A and B. The graphical representation of the intersection is only the portion that intersects the blue graph and the red graph. That is, just the purple portion. The algebraic representation of this intersection is when x is less than or equal to 2 and x is greater than -2, yielding only the real numbers between -2 and 2, including 2. In interval notation, we get the interval from -2 to 2, including 2. And in set notation, we get the set of all real numbers x that are between -2 and 2, including 2. Here are two other sets, A and B. The union of A and B is the set of all real numbers that are either in A or in B or in both. If we graph A and B on a number line, we can see that the graph in purple represents the set of all real numbers that are either in A or in B or in both. Algebraically, we can represent it as x is less than or equal to -2 or x is greater than 2. In interval notation, we have the interval from -infinity to -2, union 2 to infinity. And in set notation, we have the set of all real numbers such that x is less than or equal to -2 or x is greater than 2. The intersection of A and B means the set of all real numbers that are in both A and B. The graphical representation means the intersection of the two graphs in blue and red. However, there is no intersection between the two graphs, meaning there is no intersection between A and B. Algebraically, we represent it as x is less than or equal to -2 and x is greater than 2, which yields the empty set. In interval notation, we also get the empty set. And in set notation, we use the empty curly bracket for the empty set or the symbol for the empty set. Here's a piecewise-defined function. Piecewise-defined functions are functions that are defined in pieces. In this example, f of x is defined in 3 different pieces. We can make tables of values for each part of the graph. Starting from -4 to 2, we find values for the first piece. I will mark points -4, 3 and -2, 3 with solid dots to remind myself that the endpoints of this piece are solid dots because they are included. Using these points, we graph the first piece on the grid. Starting from -2 to 1, we find values for the second piece. I will mark points -2, 2 and 1, 1 with open dots to remind myself that the endpoints of this piece are open dots because they are not included. Using these points, we graph the second piece on the grid. Starting from 2 to 4, we find values for the third piece. I will mark point 2, -1 with a solid dot and the point 4, 3 with an open dot to remind myself of the type of dots I need to plot at each of these endpoints. Using these points, we graph the third piece on the grid. Putting these three pieces together, we have the graph of a piecewise-defined function f of x. Here we want to evaluate a rational function f of x. To evaluate f of -3, we simply input -3 for every x we see in the function. Simplifying it, we get 15/5, which simplifies to 3. Similarly, to evaluate f of -2, we put in -2 for every x we see in the function. After some arithmetic, we get a non-zero number divided by 0. However, we cannot divide by 0, so f of -2 is undefined. Here is an application. Tom is a software salesman. Let P be Tom's total pay in dollars, and N be the number of copies of Math is Fun he has sold. Tom has 130 copies available to sell. Suppose that P equals 30N plus 240 gives P as a function of N for these available copies. Identify the correct description of the values in both the domain and range of the function, then for each choose the most appropriate set of values. We're given that P is a function of N. We can also see that the equation defines P in terms of N. So the independent variable is N and the dependent variable is P. And domain is all acceptable values of N, that is, all whole numbers from 0 to 130, and the range is all possible values of P.